Good. So let me put my timer on and we can start. Hi everyone, thank you all for being here and for the opportunity to give this presentation. So it should be around 40-50 minutes, and I will be talking about hyperbolicity of general relativity in Bondi-like coordinates. And let me try to use these fancy tools. Vanishing pen and such. Right. Yeah, so I will be talking about hyperbolicity of general relativity in Bondi-like coordinates, and sorry, I'm just trying to. Anyway, and the talk is based on these two papers here that we put out in collaboration with David Hills and Miguel Zilhão, my PhD supervisors, and together with Nigel Bishop and Dennis Polny from South Africa. So the plan is the following. The talk is, let's say, split in three parts, in a sense. The first is background and motivation. So what I want to say a few words about numerical relativity, some elements of partial differential equations that we will need for the talk, and what are Bondi-like coordinates. So, since we're a diverse group, if you don't know anything about any of this, well, at any point, just interrupt me, and it's better if we say less, but we are at the same page. And then the main part is split in two, is the main result about hyperbolicity of GR in Bondi-like coordinates and implications to the well-posedness of the characteristic problem in GR. And I hope by the time we reach there, you will understand what this means, the characteristic problem, if you don't already know. If there is time in the end, we can talk also a bit about numerics and convergence. So let's start with numerical relativity, which is the topic in which the subfield, if you want, where I'm working most of the time at least. And the goal of this field is to provide solutions to the Einstein field equations. So these are the equations. The right-hand side has to do with matter sources or matter terms, the stress energy tensor. The left-hand side has to do with the geometry, and lambda is the cosmological constant. For the rest of the talk, or when we go into the technical part, keep in mind we are going to drop the right-hand side. It's going to be vacuum spacetimes, and mostly we're going to focus on spacetimes with vanishing cosmological constant, asymptotically flat. And in that case, in vacuum spacetimes, you can also, in general, you can consider the trace reverse form of these equations, but it's particularly useful in vacuum because it basically means that the Einstein equations can also write just the Ricci tensor being zero. Okay, so at some point you will see things like that, and I will repeat it. Now, there are plenty of scenarios where you try to solve these equations. So these are second-order partial differential equations. And in general, sometimes you can find analytic solutions, but in general, it's hard to find them. So there are various different approximations you can do. There can be perturbation perturbative approximations, and there are also approximations that are numerical. So that's what numerical relativity does. Choosing a specific setup. Typically, you employ this method when the setup you want to study is very dynamical, when it doesn't have symmetries that you can use, and so on. So the point is that these are still approximations, but typically you're interested in cases that are very dynamical. So you want to do some sort of time evolution. For instance, here you can see this cartoon if you want. And you can consider a system of two black holes. They rotate in a binary, they emit gravitational waves. So you somehow build a system that you evolve in time, and it tries to give you an approximate solution for this space-time that has two black holes moving and colliding and emitting gravitational waves. So as you see, here, what we're going to discuss, and we're going to focus into setups that require time evolution. And This type of systems, the PD systems associated with time evolution, are typically hyperbolic systems. You can split PD systems, you can classify them into hyperbolic, parabolic, and elliptic. Both parabolic and hyperbolic have a notion of time, but what's important is that hyperbolic systems have also a notion of finite propagation speed, where signals, let's say, propagate at finite speed. So that's something crucial in GR because you have causality and so on. Another challenge that we're not going to talk much about is basically when you want to find approximate solutions to that, at some point you need a computer. You want to put things into a computer which has a finite memory. So you will have to choose a finite region of space and time that you want to approximate. And there are various techniques and various issues over there, but we're not going to talk much about this. What we're going to focus on is on hyperbolic systems, and in particular on the choice of gauge or coordinates and how it affects the degree of hyperbolicity of these systems. Here I just want to say that these equations, if you don't choose any coordinates, they don't have a particular character. They're neither hyperbolic, parabolic, nor elliptic. You have to choose some gauge, and then you form sets of equations that have a character. And this character can be also mixed. But again, we're going to talk about hyperbolic systems. So, since we're going to do that, I have to tell you what I mean by hyperbolicity. And to make things as simple as possible and concise, we're going to focus on first-order linear systems. You can write them in this compact form. This vector u here is the state vector of the system. So here you collect all the unknowns for which you want to get a solution. These square matrices A mu are called principal part matrices, and they collect coefficients of derivatives. And this vector S here is source terms. So all terms that don't have derivatives. Now, to understand what is the degree of hyperbolicity of this system, you have to study the structure of these matrices. And the way to do it is you have to construct the principal symbol. So the principal symbol you can construct in this way here. And it's crucial that the time principal matrix is invertible. And you can construct this matrix for every arbitrary spatial direction. Okay? So once you construct that, then what you want to do is you want to understand its structure. So you want to understand. So you can classify this hyperbolic system in the following ways. These are the ways we're going to at least to use. Now, if the principal symbol has real eigenvalues, then the system is weakly hyperbolic. So real eigenvalues for every spatial direction. Okay. And here the whole discussion is for real variables and real coefficients, and everything is real. If this matrix, furthermore, is diagonalizable in every spatial direction, then the system is called strongly hyperbolic. So these are the two notions of, or two degrees of hyperbolicity that we're going to use throughout the conversation. Okay. Just to stress here that if the principal symbol is non-diagonalizable in one spatial direction, this is enough for the whole system to be only weakly hyperbolic. Okay. So these are the elements we need from here. Now, why do we even care about hyperbolicity? Okay, one way or one reason would be that maybe you have some mathematical curiosity about PD analysis and so on. But another, if you want more practical approach, in a sense, is because hyperbolicity is connected to the notion of well-posedness. Now, well-posedness is a property of a PD problem. Which depends continuously on the given data in a suitable norm, which is something that we will discuss more about later in the talk. Then this PD problem is called well-posed. Okay, so this is a property. So how it's related to hyperbolicity? If the system for which you are solving the problem is strongly hyperbolic, then it has a well-posed initial value problem in the L2 norm. The initial value problem is what you solve if you only give initial data. Let's say you have some space-like hypersurface, you give some initial data, there are no boundaries, you evolve in time, that's the initial value problem. I will also call it Cauchy problem, although maybe I'm abusing terminology. And the L2 norm is a norm that is commonly used in PD analysis, and again, we're going to say a few more words later. Now, if the system is weakly hyperbolic, then it has an ill-posed initial value problem in the L2 norm. And why we care about well-posedness? Because when we get a numerical approximate solution, then this solution can only converge to the continuum solution, so the true solution if you want the problem, if the problem we're solving is well-posed. So this means that once you increase resolution more and more, your error drops, and the solution you get, the approximation gets better and better and gets closer to the true solution of the problem. This is only possible when the PD problem is well posed. Okay? So that's the reason we do all this, to address this issue, whether or not this is true. And now let's take a look into the physics of the problem. Why, do we even care about these things? One timely and physical motivation for the systems we're going to discuss is because they can be very useful when one wants to do waveform modeling with high accuracy. For instance, one method that one can use is the Cauchy characteristic extraction, and it works in the following way. So here we have part of the conformal diagram of an asymptotically flat spacetime. This is future null infinity. This is where light rays go to. This is spatial infinity, so all space-like hypersurfaces end here. And this is future temporal infinity. Okay. Now, you can consider this Cauchy domain to be something like the cartoon we had earlier with the two black holes orbiting around each other. And you can have some space-like foliation here, where you have a system that produces gravitational waves, right? And then gravitational waves in GR travel at the speed of light, so they will go to future null infinity. So, in modeling, this is where you expect your detector to be. So you would like to compute things here so that you don't have errors, systematic errors. If you only have Cauchy domain in which you solve the problem, then you can do some sort of extrapolation to read off what you get here. And then there are systematic errors. Instead of this, you can do an extraction method where another part of your space-time you formulate it with null hypersurfaces. So you have a foliation, but instead of space-like, you have null hypersurfaces. So it's a particular choice. And this is the characteristic problem in GR. And what you can do is you can pass the information from this domain to this domain, and then you can propagate it at infinity. So you can surpass extrapolation error, and this can be a systematic error. If you do that, then you can hope to have highly accurate waveforms, and they can be useful if you want to, understand better what are the properties of the system. Maybe there are depending on the physics you're trying to capture, maybe you get small effects that can hint towards new physics in a sense, right? But again, the whole discussion here is in vacuum GR. Now, another class of studies where these setups can be very useful is when one tries to model strongly coupled matter through holography. And this is one line of research I've been working with many people together. So what you do there is that now you go in asymptotically asymptotically anti-de Sitter spacetime, and the geometric setup ends up being the same in the following way. The asymptotics of your spacetime, the asymptotic boundary in a conformal diagram, is a time-like boundary in comparison to the flat space where you had segments that were null and 2 points. Right? Now here you have a time-like boundary. In the previous case, you had inside the time-like boundary, inside your bulk. And here you can have some radius where you truncate your domain, some finite radius. And you can also put some sort of non-compact horizon, so some black brane. Then if you foliate this region of the spacetime with ingoing null hypersurfaces, then basically you end up with the same geometric setup, okay? So you have, again, the characteristic initial boundary value problem, because there is also this boundary. And in this case, you solve the Einstein equations in the bulk, maybe with some extra fields like scalar fields. And then through holography, you map these solutions to a strongly coupled model that you have on the boundary. And for instance, you can model phase transitions, where here you see, basically here we're modeling something that I think is called the spinodal instability. You can start with some configuration where everything is homogeneous, and then there is some long wavelength instability, and then you can go all the way to something that looks like a bubble in a sense. There is high energy density region and low energy density region. And such scenarios can happen also putatively in the early universe if you have beyond standard model physics. And then you can again try to compare these things with experiments to see if you have captured some physics with all this business. Right. So that's basically from the motivation side. And now for the rest of the discussion, we're going to go back to the math, okay? And the properties of these PDEs.
Thanasi, before we go there, I have a question, maybe a silly one, but it seems to me like this method is only applicable outside of the black hole horizon. Is it correct?
In what sense? You mean the method of holography? You mean?
The method of trying to understand how, using this method, for example, going asymptotically to the boundaries. Because if you're inside the horizon of a black hole, I think necessarily you end up in the singularity. And then this is not, in the singularity, the space is not really hyperbolic, so it's not, you cannot go with geodesics through the singularity. So my understanding is that when you want to understand how this wave function or whatever evolves, this could only be understood outside the horizon. Is it correct?
Right. Yeah. So now you're talking mostly about this setup, right?
Yes.
So the point here is that when you have a computational domain, so the main discussion is about the property of the PDEs and the specific property of hyperbolicity and how it connects to well-posedness. So it doesn't really rely on the specific setup, whether it has a horizon or not. So for the rest of the discussion, whatever I answer now is not very important. What's important in this question is for when you're actually trying to do numerical holography in this type of setups, you basically have an apparent horizon, right, which you want to include in your computational domain, but very slightly, such that basically you're not losing any information. So the things you extract physics from are things that are outside the horizon. So you're not really extracting any information from in here because it's causally disconnected. But you do penetrate the horizon slightly for, let's say, numerical reasons, because you do want to keep the horizon in your domain, because it might be the case that it kind of wiggles and you're losing a part just outside the horizon, which has information for, I guess, the infrared of your theory here and so on. So you don't want to miss that. But you don't want to go very, very deep, because then you have problems with the numerics. The gradients become very big and the code starts crashing and so on. So you have to be a bit careful there how you do that. But yeah, I mean, what you were saying is correct. Things from here, they will hit the singularity in a sense. But that's something that we don't encounter. We don't want to encounter singularities. Yeah, Ilya.
Okay, in the gravity part for the holography again, you have to solve PDEs. In the boundary, when you don't have the gravity, what type of equations do you actually have to solve?
Right. Right, very good. So what you do is you do solve the bulk equations, and in these cases, the bulk equations have Einstein plus Keller with some weird potential. On the boundary, in this case, we have some. There are some differential equations you keep in mind so that you know how the boundary conditions behave. What are the boundary conditions you have to, you can give. So what happens in this case, you have to do some asymptotic expansions, and from these asymptotic expansions, let's say of the metric components, you understand which are the free functions you have to choose on the boundary. Typically in this scenario, at least the scenarios we're studying, there is no boundary on the boundary, yes? So it's like 4D Minkowski, on which there is some dynamical stress energy tensor. You get the stress energy tensor from the holography dictionary, let's say, but the fall of behaviors of the metric, there are some functions that you can choose there, and some of them, they might have some equations they say. Here I'll try to clarify what I mean by Bondi-like coordinates. And, Bondi-like coordinates. Yeah. Right. So Bondi-like coordinates are families of coordinates. And as I said, we're going to focus for the asymptotically flat vacuum. Now, for convenience and for to be specific, I'm just making a choice in the language and I'm using these coordinates. I call u, r, theta, and phi. They induce a vector basis, this one. And what is common in all Bondi-like coordinates is the following. That in the vector basis, you have this vector that is null, right? This is a component of the basis. And because it's null, this is orthogonal to other vectors that are intrinsic to the null hypersurface of the foliation, or the null hypersurfaces of the foliation. So, because it's null, it's both tangent and normal to the hypersurface, and therefore that's why this is true. If you want to see, to view, the construction in terms of a metric ansatz, a generic metric ansatz can look like this. So, in a Bondi-like system, in a Bondi-like ansatz, these components of the metric will be 0. If you think in terms of the inverse metric, then this is 0, this is 0, and this is 0. The fact that this is 0 means that the hypersurfaces of constant u are null hypersurfaces. Okay? So here again, time-like boundary, let's say some null hypersurface and future null infinity, just for reference. Now, here, so what we're going to analyze is the hyperbolicity of this evolution system. So this is a system of 6 equations. They form a free evolution system. What I mean by free evolution is the following. In total, you have 10 Einstein equations in this dimensionality. Like constraints. Constraints in the following sense. If they're initially satisfied by the given data, so the boundary data, let's say, on the boundary, so at all times, and the initial data on the null hypersurface, then you can show that they will remain satisfied in the region that you're going to study. Okay? So in that sense, they're constraints. Of course, practically, when you do numerics, there is always some violation of constraints due to numerical error. But we're not going to talk about this. This can be a topic on its own. So that's why, it's an evolution system, it's a free evolution system in that sense. And we're only analyzing them. The second point I want to make is that these are 6 equations, and the metric ansatz has basically 7 functions that you need to solve for in the way it's written down. But there is some residual gauge freedom, which is the following. It has to do with what does the radial coordinate r measure. Okay? So when you have these null hypersurfaces, these are generated by null geodesics. And these null geodesics, they have a parameter. You can choose this parameter to be an affine parameter. So this is typically called an affine null gauge or an affine null coordinate system. And then once you choose this affine parameter, basically you set this to be 1. So you have 6 unknowns for 6 equations. Another choice is the standard Bondi-like gauge, where you set this coordinate r to measure the radius of 2 spheres. This is another choice, and when you do that, you're also left with 6 unknowns for 6 equations. And there are many other choices you can build in between, okay? But the common structure is if you want this third bullet here or this. Right. Any questions up to here?
So the data are on N0, but or you put data on the T.
Both.
What is but wouldn't like a point on N0 if you evolve it like hit the T surface?
Yes. Right. So let's say you put initial data, let's call them initial data on N, because the foliation is based on null hypersurfaces, and T is a boundary. Okay. So T, you give boundary data for anything that is ingoing in your domain. So this is the domain. You have you have freedom to choose everything that goes into the domain. Things that go out of the domain are part of the solution. So once you give initial data here, they propagate, and at some point they hit this. Now at this point, I don't have control over, well, I don't have control. I don't choose the outgoing part, outgoing from the domain. I only choose what goes inside. So, yes, that's correct. You expect things to hit the boundary from inside.
Okay, I see. Thank you.
Okay. Other questions? Right. Okay. So okay. This one and the next one might feel a bit heavy in words, let's say, but I hope they can be clear. And if not, just ask anything. So in the next 2 slides, what I'll try to explain is to give a specific example of the main result. The main result is that general relativity in Bondi-like coordinates is weakly hyperbolic. It has a PD system that is weakly hyperbolic. And to be specific, we're going to choose the Bondi-like gauge proper, is a specific choice. And we're going to restrict in axis symmetry, twist-free. So basically, we will have to analyze 4 equations for 4 unknowns. So the metric answer is this one. The unknowns is the functions v, veta, gamma, and u. And the PD system, so the setup, the geometric setup is the same. The PD system schematically is this one. Now, one reason that people like these formulations is the following. These systems have a nested structure. And what I mean by nested structure is the following. You give initial data on your null hypersurface, let's say the initial null hypersurface, and you give the profile of the function gamma. Once you set this, you can take this equation, where the right-hand side only depends on this derivative of gamma, which you know, and you solve for veta. In a sense, it's an ODE. If you know the right-hand side, you just have to integrate this. So in that sense, it's an ODE, but formally it's not, right? Then once you find the profile of veta on this hypersurface, then you can go to the next equation, where the right-hand side depends only on veta, gamma, and their derivatives. Similarly, you integrate for u, so on for v, and then you have the last equation, which is the genuine, in a sense, evolution equation of the system, because it's the only one that has a derivative extrinsic to the hypersurface, where you have everything you have found so far, and you take a step, numerically at least, to the next null hypersurface. And then you can repeat this process. This fact, this specific structure, allows you to have very convenient and compact codes. Like, is a sequential integration you do, and you can do in parallel. so it's easy to parallelize and you can do nice things with less resources, basically. Okay, so that's one thing that we will like, but at the same time, it can also give you some sort of confusion when you try to understand formal aspects of the system, because you might view this as a sequence of ODEs, so you might say, my problem is well posed because it's just ODEs, it's nothing complicated. But actually, when you want to do a PD analysis here of hyperbolicity, you have to view the whole system together. This is a property of the whole system. So you have to grab this thing and somehow do a hyperbolicity analysis. The way we do it is the following. So remember when I talked about hyperbolic systems, I defined, if you want, things using a first order linear system. Now this is not a first order linear system. Therefore, I have to make it. And crucially, the properties of hyperbolicity, let's say the structure of the principal symbol, it transfers from the linear to the non-linear system. So that's a crucial thing. So what we do is we take the system, we linearize it about the background, and we do a first order reduction. For linearization, for the rest of the discussion, for simplicity, I'm just considering asymptotic or Minkowski background. It's the simplest possible, but it's enough to make the point. First order reduction here is a minimal first order reduction, so I'm introducing the minimum new variables that allow me to have a completely first order system. So for instance, what this means is that I take this derivative and I view it as a variable on its own. So it has an evolution equation, and then I can use it to have an evolution equation for gamma itself, right? So that's that's a standard procedure you can do to do a first order reduction of a second. And then you can use this form to do the PD analysis. Now, I said that we're dealing with a characteristic problem in GR. So when you write your system in the characteristic frame or the characteristic setup, what you see is that the time principal part is not invertible, so its determinant is 0. In PD language, that's exactly what it means to have a characteristic problem. A hypersurface for a solution of your system is characteristic when there is this degeneracy of the principal system. So it's another way to say that this is a characteristic problem. That's expected. The thing is that since this is expected and this is here, you cannot form the principal symbol like that. So somehow you have to have a time principal part that is invertible. So the next thing is to do a coordinate transformation to a setup which looks like a space-like foliation, right? Like a 3+1 or whatever. Now this is an auxiliary problem in the sense that it is merely a tool to be able to do the analysis and to refer to standard PD language and analysis in textbooks, right? Once you do this coordinate transformation, what is crucial is that you're not changing the hyperbolic character of the system. If you remember at the beginning, I said if you take Einstein's equations and you don't choose any gauge, any coordinates, that system doesn't have any character in a sense that it's not hyperbolic, parabolic, or whatever. Now, once I choose my gauge or my coordinates, then I'm fixing the character. I'm forming a system. And then this system has a hyperbolic character. Okay. And this hyperbolic character is dictated by, let's say, the metric answer. And this is what gives the character. What I do here is basically I'm just doing linear combinations of derivatives. So I'm just splitting the null derivative into time and space. That allows me to form the principal symbol. That's all I'm doing. I'm not changing the hyperbolic character. Okay? So what I get as a hyperbolic character for this system is going to carry over for this system. Okay? Now, once I do that, then I can refer to the standard PD language and analysis. What I was describing is exactly this thing. I'm splitting this thing into these parts, and this allows me to have an invertible time principal part, and then I can have a principal symbol. Now, this system is only weakly hyperbolic because the principal symbol is non-diagonalizable in the angular direction. And that's enough to say that this system cannot be strongly hyperbolic. Only one direction of non-diagonalizability is enough. Okay. Now that's an explicit example of a Bondi-like PD system, if you want, and that's something we put out 2 years ago with David and Miguel. Now, from there on, we have done the same analysis for more systems of this family. So you can change the exact coordinate choice, like how you label the radial coordinate. You can change how you describe the two-sphere. You can have less symmetry. Instead of using spherical polars, you can use complex way of describing the two-sphere. You can go in asymptotically ADS. You can go in higher dimensions. In all cases, we saw that these systems were only weakly hyperbolic, and the structure was the same. The direction made us ask, okay, what is common in all these formulations that renders these systems only weakly hyperbolic? But to understand the answer, I have to say a few things. First, what I mean by gauge structure of GR. And to explain the gauge structure, what I mean by this, I will have to use the ADM equations. Now, in case you haven't heard of them again, it's completely fine. You don't need much. I'll tell you what you need. Now, if you think about the cartoon we had at the beginning, you had this space-like foliation, right? And typically this can be called the 3+1 because it's typically done in 4 dimensions. Now, the ADM formulation is basically a Hamiltonian formulation of GR. And the variables, the main variables of your equations are the spatial metric of your space-like hypersurfaces. This is called this gamma ij, and here I'm doing a linearized analysis, so delta gamma ij is the perturbation to the background value. It's also the extrinsic curvature kij, so it's perturbation delta kij, and the coordinate choice or gauge choice is captured by the lapse function alpha, so delta alpha is its perturbation, and the shift vector veta. So delta veta with index down is component of the covector and perturbations to that. And basically, the lapse and the shift capture the gauge choice or the coordinate choice in the ADM formalism. When you use the ADM formalism, you basically have some dynamical equations, some evolution equations. This is the system linearized about flat space. And you have some constraint equations. These are equations that don't have time derivatives. They have only derivatives intrinsic to the space-like hypersurfaces, and they're connected to Hamiltonian momentum constraints. Okay? Okay. So we have this set of equations. And if we consider a first-order reduction again, and the first-order reduction where so this is a system that is first-order. The first derivatives, I will introduce them as reduction variables. If I do that, then I will have a completely first-order system in both space and time. And if I introduce every spatial derivative as a reduction variable, I will call this a standard reduction because I just blindly, I make everything a reduction variable. Okay? It turns out that if you do this, and if you work in the linearized approximation, you are able to understand some structure in the principal symbol of the system. So this is the principal part of the system. This means I'm dropping source terms. This is a matrix, the principal symbol, in an arbitrary spatial direction. And what David Hillage and Ronnie Richter showed in 2016 is that actually here you can find some structure, and is the following. First of all, this matrix can be written in a way, well, it has this upper diagonal form, and it has some sub-blocks. Now, the subscripts, this is the pure gauge subblock, this is the constraint subblock, this is the physical subblock, and this is a coupling between these two. What it basically means is that once you get these equations, if you look at the variables you have, it's not always, you cannot understand what type of information they carry. They can carry something physical together with something else, right? In this way, in a specific approximation, you can distinguish when you look in a specific direction if the variables you have at hand, they are talking about the gravitational wave polarizations, the physical part, or if they are talking about, or if they carry information about violation of Hamiltonian momentum constraints, or if they're purely gauge effects or gauge information. Okay, so there is this structure. Just keep that. The second piece I need is to talk about the pure gauge subsystem. Now, to explain this, let's do the following. Take Einstein's equations in vacuum, so let's say this, in the case we're working, and consider some arbitrary solution, so some metric, 4D metric. And then, on top of that, consider an infinitesimal coordinate transformation, so that is a gauge transformation. So this C is small. Once you do that, the description of your solution changes by a bit, because you have changed the coordinates with which you describe it. And this perturbation to the solution can give you evolution equations for the perturbation to the coordinates themselves. Now, you can take these perturbations and you can do a 3+1 split in the same way you do an ADM one, and you get this evolution equation or this evolution system. This system gives you a relation between perturbation to the coordinates. Okay, and this is a subsystem or a system that is closed on its own. And what's important is that here you see perturbation to the lapse and the shift. And these two things are the things you choose once you formulate your equations. For instance, when you have, let's say, a 3+1 split in the ADM language, you have a problem at hand, and you don't know which coordinates to choose or which lapse and shift to choose, then, depends on the problem you have at hand, what is convenient. And you will see in a moment why this is important. By the way, this thing was first done by Hoklov and Novikov in 2001, being closed. Now, what's crucial is the following. The structure of that system is inherited by the linearized ADM equations. And more specifically, the structure of this block is exactly the same as the structure of the subsystem we just saw. So let's say this, in a compact form, is the system we saw before, for some choice of lapse and shift. So here these are just some functions. I'm just making them be some functions. So if you plug them in that system, then that system has a hyperbolic character. It's a closed system, either the principal symbol is diagonalizable or not. But exactly the structure is the same here, is inherited by that system. And why this is cool, why this is useful? Because if you have a problem at hand where you don't know what is the convenient gates to choose, you maybe have some choices, then some of them might give you a pure gauge subsystem, which is easy to analyze because it's small, which is weakly hyperbolic. If this is true, then the full set of equations, the ADM equations, linearized, are definitely going to be weakly hyperbolic at most, because this is non-diagonalizable, and because of this upper triangular form. Okay? So it's, in a sense, it's a bit economic. You can know if the gauge choice you're making has potential to give you something good. Okay? And here I try to simplify the discussion by particular choices, but you can have more complicated choices of lapse and shift, and this can still go through, right? So it turns out that if you use all this machinery in the Bondi-like systems that we saw a particular example, then you see that the pure gauge subsystem, so this PG, is non-diagonalizable in the angular directions, and therefore the whole system will be because you impose this thing. When you make the gauge choice, some components of the metric are zero. So here I'm presenting the components of the inverse metric, but the fact that this is true means that this is going to be non-diagonalizable, and this transfers in the full set of equations. Just a disclaimer here, we were able to show this explicitly for some example, for the full characteristic system, but it's in a sense is a conjecture. We don't have an explicit clue for all parts of the family. What we can show is that this is true for all parts of the family, okay, of the Bondi-like family. So this means that we think that if you take GR and you formulate it in Bondi-like gates, then the PD system is only going to be weakly hyperbolic. So this means that the characteristic initial boundary value problem is ill-posed in the L2 norm, which has implications or potential implications for accuracy, for instance, of waveforms, the CC method I described before, or other results that you do, like numerical results that you might be interested in doing or obtaining with these formulations. Right, now, I will say a few words about well-posedness, but before I go, let me know if you have questions for the previous part. I can go further back. Manto, question? Yeah.
Yes, so I don't know if this is a well-defined question. It seems like you're deriving that the system is weakly hyperbolic from just the subsystem of the pure gates, of the gate subsystem. So isn't that in a sense saying you can derive something for the physical part from the pure gates part?
So what you do by this is the following, right? You have a set of equations, is a PD system. What you're trying to understand is what's the hyperbolic character, weakly or strongly hyperbolic. You know that if you write these equations in a particular form, this ADM-like form and linearize and so on, then you can write the principal symbol in this way. And for this, and then we know for the particular coordinate choice that there is always going to be something like that, which is problematic. The only thing that this tells me is that this system has this hyperbolic character. To be honest, that's all it tells me. So, what I infer from this information is that if I solve a PD problem based on this system, then this PD problem is going to be ill-posed in the L2 norm. That's all I know. It doesn't tell me that I cannot do physics with this system in general. It tells me that if I'm getting solutions out of an ill-posed problem, so let's now assume it's ill-posed because it's a question mark and you will see. If I'm getting mathematical approximations like of any type out of an ill-posed problem, if I don't know it's ill-posed, but I'm inferring them as physics, I might be in deep problem. I might get some weird behavior, right? Something that is numerical error, but I don't know it's a numerical error that is not converging to the true solution, and I think it's something physical. Just because I don't know what I'm seeing is correct or not. So if you have a very complicated scenario where you don't know what to expect, or you know more or less, then maybe small details you might, be triggered to say this is more than it is, for instance. Now, whether or not the fact that these systems are weakly hyperbolic means that they are ill-posed in any sense is an open question. But the fact that I know the structure of this system here, let's say, or of the whole thing from the pure gates, it doesn't mean that I cannot, in general, do physics. It doesn't tell me something about this. It only tells me that, this is non-diagonalizable. That's all it tells me.
So can you still trust the simulation to get
That's
some
a
information out
question.
of it, or no?
That's an open question. I don't know.
Okay.
I don't know. I can tell you a few things I know, in the discussion, but that is an open question, an honest open question. And you will see more about this actually in a bit,
Okay.
I think. And you can ask me again after, okay? More questions?
See?
Yeah.
So here you want to basically say that this Total matrix is not diagonalizable, and then you say, okay, if I show that one block is not diagonalizable, then so maybe I didn't get this in the discussion, but why is that specific block easier to see? That's not
Right.
diagonalizable.
So, assume for a moment that, if you take the linearized ADM equations, then you can write them, you can have this form, okay? Let's just accept that for a second. Now, I didn't show how you see that, but the claim I'm making, and it is in this paper, is that if you take what is called the pure gauge subsystem, which is something you can form like that, this is linearized about flat space. The system can be more complicated, but essentially is a first order linear system. So you can take a system that is small, is not the full set of equations, and you can take this smaller system, which has a particular structure, and you can try, let's say, in general, different gauge choices in terms of lapse and shift. This system, when you make different choices of lapse and shift, will have potentially different hyperbolic character. Now, in the Bondi-like coordinates, it has a particular character, which is weakly hyperbolic for a particular reason. This system itself, the pure gauge subsystem. And the fact that the structure of the pure gauge subsystem is inherited in the full system tells me that if I want to formulate a characteristic problem in the ADM language, so linearized now, then that system is going to be weakly hyperbolic. Now, a question here is how this ADM-like language or set of equations is even related to the original characteristic system that has this nested structure and so on. And that's a valid question because it's not straightforward that they are. And then you have to jump through some hoops and you have to map variables and you have to do coordinate transformations, and effectively, or finally, you show that you can map one set of equations to the other. There is a correspondence in a sense. So then you expect that this structure will follow whatever hyperbolic character you get here will follow there. There are more technical details and there are some very interesting details that I'm not saying, but if there is time later, I will tell you. There is, let's say, an asterisk where there is some structure you're missing in the characteristic system. I can tell you more.
Okay, we can discuss in the end.
Yeah, but does it make it more clear what you asked? Did
Yes.
I answer? Okay. More questions? Okay. So I'll try to be a bit brief to give the essence of, why all the things we said before should matter in some practical sense. And for this, we're going to talk about well-posedness, and we're going to use toy models to make our life simple or simpler. Okay, so these are toy models that, we will formulate a characteristic problem. It's just a toy problem. And just for reference, this is the system. This is the null direction if you want. It's a compactified direction, like in a sense you can reach null infinity for whatever this toy model has. This is the transverse direction, this is time. That's one thing. The second thing is that they do have a nested structure depending on the choice of sources. Okay, so let's say these are homogeneous, then this system has a nested structure. Now these are basically two models in disguise. If you remove the box term, then that system is strongly hyperbolic and that system is well posed in the L2 norm. Now, just to see what I mean by L2 norm is that this is the state vector, and the L2 norm basically is an integral where in the integrand goes everything that is an unknown, like square, okay? And the domain in which I'm integrating, let's assume for a second that I'm doing an initial value problem. Then that domain would be a space-like hypersurface and everything would be in the integrand. Now, if I'm doing a characteristic problem, I have to be more careful because the geometry of the problem and what propagates inside or outside or left or right affects the integrand, but we're not going to go in details now. But morally, something like that is the L2 norm of the strongly hyperbolic system. On the other hand, if you include this thing, you have a weakly hyperbolic system for the same reason as the Bondi systems. The principal part is non-diagonalizable in the angular or transverse direction, just because of this thing. Now, somehow you can see that this system, in fact, has a norm in which it is well posed, the problem we want to solve. And again, let's consider a space like hypersurface, the domain, and then what's modified is instead of just having the L2 norm, you're actually adding in your norm this derivative here. So this basically means that because I have this thing that makes the system weakly hyperbolic, somehow when I give data, I have to control this data and the derivative of this data in this direction. So I need to control more. Now, of course, this is a particular setup because when you have a weakly hyperbolic system, it's a question whether or not there is any norm that this system is, well, gives you a well-posed problem. And it's a slight, or is a weaker sense of well-posedness because actually it's affected by source terms. So here, if I break the nested structure, if I choose some sources that break the nested structure, this system becomes ill-posed in any sense. There is no norm that can do, like, you can serve well-posedness. So even if you have a weakly hyperbolic system that is well-posed, that's a weaker notion, and it is affected by source terms. Furthermore, now we're talking about first-order linear systems. These systems, you can think of them as coming from a linearization process of a second-order system that is non-linear, and so on, like we discussed before. So all these steps of linearization, so the non-linearities, they can also break weak well-posedness, whereas this is not true in strong well-posedness. It's not affected by source terms, it's not affected by non-linearities. These are results that are in PD theory, in textbooks, which I don't know how to prove, but they're there, okay? So, you know, this is an explicit example, if you want, of how a norm would look like for these cases, or for like an L2 norm would look like for a model, or a lopsided norm. I call this the lopsided norm because you just add this derivative, not every derivatives. Right, so this is, you know, how hyperbolicity can affect well-posedness. Now, let's do a quick recap and see, you know, what I think is important to keep as a main message, which is the following. If you take GR and you formulate it using a Bondi-like gauge or a Bondi-like coordinate system, so you make a free evolution scheme, that's what we analyzed, then this system is weakly hyperbolic. And the root of this with hyperbolicity is the pure gauge structure. So the fact that you're having a metric ansatz that has this property here. In a more pictorial sense, this can be translated in the following way. Consider a two-sphere of constant radius. And here you can see this two-sphere being pierced by outgoing or ingoing null rays. Okay? Each of these rays or geodesics is labeled by some angular coordinates theta and phi. So if this outgoing trajectory pierces this two-sphere, it will be labeled by theta1, phi1. And if it pierces a sphere with a bigger radius, it will still go through the point theta1, phi1. So pictorially, if you want, this thing means exactly that. In other words, it's some sort of lead dragging of the angular coordinates along the null geodesics. But it's this structure which is very intuitive and very simple, like you should expect to have something like that. It makes sense. But it seems to be exactly this structure that to the PD level causes weak hyperbolicity. In other words, you know, you don't know if you had something like a shift, if you would pierce these two spheres in different points along the geodesics, if this would be true. This we don't know. And this C here are coordinate light speeds. So this translates into C theta and C phi being 0, for instance, this shift. Now this has implications on well-posedness, which means that the initial boundary value problem or initial value problem, when formulated with these coordinates, is ill-posed in the L2 norm. Whether or not there are other norms, that's an open question. This has implications to the accuracy of numerical results and how much we can trust them. Again, is an open question because we don't know if there are other norms. Now, before I close, that's the last, I think, slide, should be. I'll leave you with an open question which has to do with this norm. Now, we know that there are results where you can take GR and formulate the equations with higher order derivatives. Somehow you can do it. You can go in third order derivatives, and you can use these coordinates, and you can get PD systems that are symmetric hyperbolic. So namely, in this case, you are using the contracted Bianchi identities as well. Now, since you have a symmetric hyperbolic PD system, which is better than strongly hyperbolic, then you can actually show that the PD problem, characteristic PD problem that is based on this formulation, which has higher derivatives, is well posed in the L2 norm. Now, this L2 norm is a different, is the L2 norm of that system. If you write that system in first order form, then the variables, they have second order derivatives. Whereas in the previous system, the system itself was going up to second order derivatives. So nothing like that would go in the norm. So the question is, okay, can we infer from these constructions a lopsided norm, some sort of weird norm, where the systems we analyzed are well posed, or their PD problems? And that's something we're trying to answer, and has a few technical problems, but that's what we're working on now. And I think I stop here. Yes, that's the counting is wrong. Thanks. And questions, just unmute and ask.
I have a question, if there's no one else more urgent. So I heard a troubling statement, and I think it was in 9 of 17.
Here.
Yes, right. So you have this matrix, I presume AU,
Yeah.
which is not invertible.
Mm-hmm.
You're doing some kind of coordinate transformation, and you end up with an invertible matrix.
Mm-hmm.
And I'm trying to reconcile how is that possible in my head. I mean, if I think of the transformation as a similarity transformation, then this shouldn't be possible.
The basis change. If you that's what you're asking.
Yeah.
Yeah, it's not a change of base. It's a different way to write the differential equation. But yeah, okay, that's can answer.
Yeah, no, it's exactly what Pantelis is saying in a sense. So when I'm writing here, okay. So when I'm writing here this thing,
Yeah.
this is a derivative that has both time and space inside. It's a null derivative.
Okay.
So what I essentially am doing here is I'm just taking this derivative and I split it into the radial and the time part. So I'm just, doing a linear combination of derivatives. Instead of doing del t plus del rho equals del r, I'm splitting del r. Just by doing that, I'm basically, forming a matrix that is associated with time that is invertible.
Okay, now I see what you mean by that. Yeah, okay.
Is basically, in a sense, linear combinations of the derivative.
It's more like a, yeah, okay, I got it. Thank you.
Okay, so, and this is necessary here. Well, I mean, there is some work on how you can do it directly in the characteristic system. By that time, I didn't know it, but essentially, even in that work, they use methods like that. This is the work of Fritelli.
Oh,
and actually, go ahead.
This was the point kind of where I joined. I was a bit late, and I didn't actually catch up the definition down there for what AT actually is. I mean, even it's immediately obvious that this is possible.
Yeah, okay, so exactly. The point is that maybe, so okay, if you join here just to, in the sense of hyperbolicity, I'm not sure if you're familiar, if you just have a linear system and you want to do some hyperbolicity analysis, this is a first order linear, I'll call it hyperbolic.
Yeah.
Then you want to build this matrix, but to build this matrix, you need this other matrix to be invertible. And in a characteristic problem in the PD language, this is something you expect because the characteristic problem basically means that. So directly in that problem, you cannot, form that system. So that's what we did here. Okay.
Yeah, thank you.
No worries. Ilya, did you have a question or someone else? I saw a hand. I don't know if it was wrong.
No, it was me.
Okay. Yeah, other questions? Was it too fast? Was it too slow? Sorry?
I found a bit too fast. I mean, not too fast, but a bit fast.
Okay. Maybe it was too much information.
Yeah. So I would like to ask
Okay.
basically recap on pages 8 and 9. I lost the yeah. So I lost the point. So you said, okay, this is some nested
Right.
problem, and I lost the point in the last equation where you said that when I solve the last equation, I move to the next null surface.
Yeah, okay. So to be honest here, maybe that was an overkill, but I will explain what I mean. The description I was giving was more, let's say, to give you a taste of how a code would work for this thing. In the following sense. If you see the first three equations, they only have derivatives that are r or ij. By ij here I mean, I think I mean theta and r, but okay. The point is that the first three equations, they only have derivatives that are intrinsic to the null hypersurfaces. Okay. In a way, in PD language, you can call them constraint equations because they're constrained within the hypersurfaces of the foliation. But really, they comprise the evolution system here. So what it means is that you give some initial data. From that, sequentially, from the nested structure, you figure out the other unknowns that you don't have. And then you have this equation, and this equation has a derivative, del u, that is extrinsic to the null hypersurface. So what you do is if you think in terms of a null foliation and a code that goes from one hypersurface to the next, then you use this equation, you know everything on the right-hand side, and you use some sort of time step, some numerical method, to take you from n0 to n1. In n1, by solving this, you know gamma. With gamma, then you do the same thing over and over again. And this is a bit different than what is typically done if you have a space like foliation, where you have a bunch of unknowns, all of them have evolution equations, and in this hypersurface, you give like 5, 10, whatever functions, and then you take a step forward and step forward for all of them together. This is more heavy numerically. So with this, you can do, let's say, if you don't have many resources, you can still do some nice stuff. But that was maybe an overkill.
Oh, it's fine. I understand.
But also another point I was trying to make here is that it looks like ODEs in the first three equations, at least morally. So I have heard in the past the statement that since these are a bunch of ODEs, people expect the PD system to be well posed. And for these PD systems, people had already shown existence and uniqueness of solutions. So what was left was continuous dependence. Now, a bunch of codes work very well with these things. Like, in a sense, they're stable, like you don't see them crashing and so on. There are some convergence tests that work. So people were expecting that these problems are well posed. But actually, we see here, because of hyperbolicity issues, that is not so straightforward to say. There might be, it's an open question, but they're definitely not in whatever is the L2 of these systems. So we try to find other norms to show continuous dependence and talk about well-posedness. So this means that once you get numerical results, then, they're not undisputable. You can say, okay, how do you know they're correct or not? So there are a bunch of things there. And I'm saying that myself, I'm producing numerical results from a bunch of these things.
I mean, I have a small question related with this. Can you compare your numerical results with some analytic results and see whether or not this is the case?
Yeah, they reproduce them. But the point is, in principle, it might be some corner of the phase space of solution where this behaves well. I mean, you cannot guarantee. So it's some sort of you're trying. We don't have a proof. We have expectation. We have evidence. We're trying to some sort of bridge them in a way by studying these things. But yes, we can reproduce and in different setups, both in ADS and in asymptotically flat. Well, ourselves in the collaboration for holography, other people that do waveform modeling. There is a lot of benchmarking against other codes and analytical results or other stuff, which is very good. But again, as a matter of principle, we don't know for a fact. Right. Shall I stop sharing? Are there more questions? Is there anything you want to discuss other than that?
Let's keep asking. Nobody else has something.
Okay, then maybe I can stop recording and then discuss more.
Good. Okay. Thanks. Thanks, guys. I'll stop.